We continue our discussion of limits by now examining limits as applied to rational functions. So let's go ahead and examine this limit theorem down here at the bottom. All right, it says if p of x and q of x are polynomials and q of c is not equal to 0, then the limit as x approaches c of p of x over q of x is just p of c over q of c. What this is saying is that you can plug it in so long as the denominator is not equal to 0. Okay? If the denominator is equal to 0, then you have to algebraically manipulate. Okay? So that's going to be a requirement here. We're going to have to check that out. Okay? So if we see a problem in plugging in, we're going to have to try to manipulate algebraically. So let's take a look at number 5. So if I know that I plug in 6 right here, I'm going to end up with 6 minus 6, which is 0. I have a problem. So what I'm going to do is I'm going to try to manipulate this algebraically. And unfortunately, the only thing I know how to do right now is I'm going to break it up like this. Okay? Because it's a binomial squared, right? Break it up like that and see if I can eliminate a factor. But in this case, as far as x plus 6 is concerned, I can't cross anything out. So unfortunately, this is one of those cases where we can easily say then the limit does not exist. And that's the problem, is that you're going to want to think right away that the limit does not exist. And some of you, that may be your go-to answer right now. And unfortunately, that's not the case always. All right? You can't always just assume that it doesn't exist. Let's look at number 6. All right? I can easily assume on number 6 here that the limit does not exist because clearly I'm going to plug in 0 in the denominator, right? And I have 0 in the denominator and it doesn't exist, right? That is a wrong or false assumption. All right, in this case, we have to do what we said over here, and that is algebraically manipulate. So in college algebra, you work with something similar to this. We talked about complex conjugates, but we're going to talk here about the conjugate. So what is the conjugate? Okay, so let's talk about that. If I have, for example, a plus b, its conjugate is going to be a minus b. All right? When you multiply a plus b times a minus b, you get something called a difference of two squares. Now, I want you to verify this by FOIL method, that when you multiply this times this, you get this. It is a difference of two squares. I call this dots. Okay? My students often remember this because it is my favorite candy. Difference of two squares. All right? Dots. All right? So what I'm going to do is I'm going to set this up. So I'm going to say, okay, well, let me manipulate this algebraically then. I'm going to multiply then by the conjugate. So 1 plus x, that's fine. But you notice here it says minus 1. So the conjugate is going to say plus 1. All right? And then you're going to do the same thing on the bottom. Because remember, you can't really just multiply by anything. The only thing you can multiply by is 1. Or in this case, a factor of 1. Because this divided by this is 1 exactly. Makes sense? So we're not changing how much it's worth. We're changing the way it looks. And what I do is I always tell my students, I give them the analogy. I said, what we're doing is we are creating, what you have here is like the scenario where if you have a dollar bill and I say, I'm going to swap your dollar bill for the change that I have in my pocket, okay, and I give somebody 4 quarters in exchange for their dollar bill, I have not changed how much it's worth. It's still worth $1. I've only changed the way that it looks. Okay, so let's take a look and see what happens with this problem. We have created a case of the difference of two squares. So we're going to square this. That's your a square and that's your b square. All right, when you square a square root, you get rid of the square root. Okay, so you have the limit as x approaches 0, and you have to keep writing that. Keep that in mind. You're going to have 1 plus x minus, okay? Now, when you square 1, you still get 1, okay? And then in the denominator, you're going to have x times the square root of 1 plus x plus 1, okay? So no big deal there, okay? So 1 plus x minus 1, what I'm actually going to do here, because I have the luxury of this fancy digital pen, all right, is I'm going to get rid of the parenthesis. 1 plus x minus 1, and now let me switch up my color here. Let's see here, pick a red pen, get rid of that. Okay, so I end up with something that looks like this, all right, x over, and I almost forgot something. I didn't take my own advice. The limit as x approaches 0 of x over x times the square root of 1 plus x plus 1. Okay? Now, you should notice something. Common factors can be eliminated. All right? You cross out the x divided by the x. And actually, I picked the wrong color. Let's do that again. Let me find my red pen here. Oh, come on. There it is. There we go. And you're left with a factor of 1 on the top. So now, Theorem 3 applies. Because can you plug in 0 without an issue? And the answer is, yes, you can. All right? You can do it. Okay? So what we're going to do is, and give me 1 second. What we're going to do is now we're going to plug in the 0. All right? Now it's safe to plug in the 0. So I'm going to get something like this. 1 over the square root of 1 plus 0 plus 1. Well, 1 plus 0 is 1 and the square root of 1 is 1. So I'm going to be left with 1 plus 1, which is, you guessed it, 2. So the limit is actually 1/2. Again, remember, way back when over here, it looked like the limit did not exist, but the limit is actually 1/2. And if you look at the graph of this rational function here, you'll actually verify that it is actually 1/2. What happens is this graph has a hole in it. Okay? Let's go ahead and take a look at another problem. In this next example, again, you try plugging in 6 in the denominator and you see that you have an issue. So we're going to try again algebraic manipulation. All right, so what I notice when I look at this problem here is that this top can be factored. And this is again what I call dots, a difference of two squares. You can break it up. There are two squares, they're being subtracted, hence difference of two squares. So you take the square root, x plus, and then x minus, and then the square root of 36 is 6. So it looks something like this, and then you have x minus 6, of course, that was still in the denominator. Now, take a look and see what happens. Reflect on that for a second, okay? You might notice that the x minus 6 crosses out. Now we're left with that previous theorem that we've discussed, which is that you could just plug in. So now we're set to plug in and evaluate the limit. So it looks like this. I'm going to rewrite it because it's now simplified. All right, but yes, now we can just simply plug in. Okay, so you want to get these so you can set them up to plug in, and you end up with something very simple. 6 plus 6 equals 12. All right, let's take a look at another one. Number 8 here. This one, another one that when you plug in 2 in the denominator, you get 0. So we don't want 0 in the denominator. We're going to factor again and see if we can't eliminate something. So we want the factors of negative 10 with a difference of positive 3. All right. Well, I'm thinking 5 times 2 is 10, and the difference of 5 and 2 is 3. So one of them is going to be negative. And I'm going to say, okay, well, the limit as x approaches 2, and that's how you read it, the limit as x approaches 2, right? And I'm going to say, okay, x minus 2 and x plus 5, because 5 minus 2 is a positive 3, and negative 2 times 5 is a negative 10. And then we're left with the x minus 2 in the denominator, and you should start noticing what's going on here. All right? Notice what's going on. What happens is that you can eliminate the x minus 2. Okay? You can eliminate the x minus 2 here. And so when you do that, you end up with the limit as x approaches 2 of simply something like x plus 5. And it's, again, something that you could just plug in and evaluate. All right? And you end up with 2 plus 5, which is 7. So really, really simple after you factor it out. The last one here, number 9, is a really neat one because you have to factor out the numerator and the denominator. Because when you think about it, when you plug in 4 here, you're going to get 16 minus 16, which is 0. So it's necessary to factor numerator and denominator in this case. So I'm going to go ahead and do that. Now I'm a little bit faster probably than most at factoring these. I have the 32, negative 32, and we want a difference of positive 4. All right, 8 and 4. I'm going to say x plus 8 and x minus 4, and that's it factored. So again, as I've mentioned before, the weakest calculus student is the weakest algebra student. Your algebra needs to be there. Notice the skills that we're using, factoring, multiplying, and things like that. This right here is again what I call dots, a difference of 2 squares. I'm going to have x plus 4 and x minus 4. Okay? And then I'm going to check, okay, now can I eliminate anything? Okay? So when you think about it, yes, you can eliminate something. The x minus 4s, you have that in common numerator, denominator, you can cross it out. All right, you're left with the limit as x approaches 4 of x plus 8 over x plus 4. And when you look at it, can you plug in the 4 now without getting 0 in the denominator? Certainly you can. 4 plus 8 over 4 plus 4. This works out to be 12 divided by 8. You can reduce that to 3 over 2. And there's your limit. So look at all of these. It looked at the beginning like the limit did not exist, but after manipulating them algebraically, the limit actually does exist. Okay? You've got to do some algebra here. So if this video was helpful, as always, remember, like and subscribe.